talk. Unfortunately, Binyi Chen couldn't make it because couldn't get the visa on time. So this will be a pre-recorded talk. So while we set it up, we understand, of course, if you need some time and you prefer to change room. Okay, so we'll now set it up and play the talk.
Hello, everyone. It's a pity that I cannot come to Rome in person due to visa reasons. So today, instead, I present remotely. My name is Binyi. I'm currently a postdoc researcher at Stanford. Today, I'll present Symphony, which is a new efficient proving paradigm using accumulation and folding schemes. The ultimate goal of this talk is to build better SNARKs. SNARKs are a powerful cryptographic scheme that allows a verifier to fastly checking the correctness of complex computation. Nowadays, we've seen many new exciting applications of SNARKs, such as verifiable machine learning, ZKVM, and online digital provenance. All these applications require proving large statements. And we want the proof generation to be fast, memory efficient, and it would be nice if it can be post-quantum secure. A key observation is that all these large-scale applications involve iterative computation. Well, a single computation unit is executed repetitively for many times. For example, in ZKVM, this will be a single CPU instructions or a chunk of multiple CPU instruction steps. In LLMs, this could also be a layer of token inference and so on. So this computational model will be the focus of today's talk. And proving it is equivalent to proving many uniform statements with the same circuit structure. As a side note, I want to mention that even for general statements that are not iterative, we can apply some compiler to reduce it to uniform statements. So our main task today is to be able to prove many uniform statements in a batch. Efficiency-wise, we want a fast and memory-efficient prover, and we want proof size to be as small as possible, like polylogarithmic in the length of only each single individual statement. Security-wise, we want scheme to be plausibly post-quantum secure. Towards this goal, researchers recently introduced the notion of accumulation or folding schemes. So there are a public coin interact protocol that reduce the checking of multiple NP statements into the checking of a single statement. As you may see, the output statements here is not necessarily succinct. So folding is a weaker primitive than SNARKs, which does not give you full succinctness, but it also leads to fast construction and better proving efficiency. Additionally, you can make folding protocol non-interactive via the Fisher-Shamir transform by computing those verified challenges as the hash of the transcript. Folding schemes are a powerful tool for constructing incremental verifiable computation, or IVC. IVC is a scheme that allows a party to dynamically prove the correctness of many steps of computations. But the proof size and the verification here can be independent on the number of steps you prove. For example, suppose your goal is to prove a chain of computation of some function f. IVC allows you to achieve this in a streaming and memory efficient fashion. At each iteration step, the prover folds the two current statements into one, and then it generates a new online statement justifying the correctness of the previous folding step, as well as this new step of unit computation. You do this many times. In the end, the correctness of the last folding statements would imply that all previous online statements are true. So now it suffices to prove these last statements for which we can use a standard SNARK to compress it further. More generally, we can fold using a binary tree, or even support arbitrary DAGs of computation using the so-called proof-carrying data schemes. PCD and IVCs are really elegant and generic paradigm to support low memory proving. However, it has several drawbacks. First, the statements to be folded here includes both the unit computation F and also the folding verifier circuit, while the latter contains many hash function gadgets to be proved because of the Fisher-Shamir transform. And this hash gadget sometimes can be expensive to prove. In lattice folding schemes, even for 2-to-1 folding, if we use Poseidon hash, the verifier circuit can still take about 100,000 R1CS constraints over a field because in our case, the commitment we use are ring elements that have high degree. And this could be worse in a hash-based folding scheme, which leads to open many Merkle paths. Second, this also leads to some security concerns. First, non-interactive folding is only proven secure in the random oracle model. So after we instantiate this hash function in the circuits, we are no longer in the random oracle model, and the IVC scheme security have to rely on heuristic conjectures. To address these issues, we introduce a new proving paradigm called Symphony that uses folding and accumulation schemes in a different way. To my knowledge, we know SNARKs based on folding-like techniques, but this I think is the first paradigm that directly uses folding and accumulation schemes without IVC or PCD. Compared to IVC, moreover, we can recover the security proof in the random oracle model. Of course, we can also do monolithic SNARKs, but compared to monolithic SNARKs, our paradigm enables a more generic approach to achieve low memory proving. And on the other hand, our paradigm also makes use of monolithic SNARKs in a black box way, but is only used for proving a much smaller statements. Finally, this work already has some real-world impact. 0xPark is adopting our range proof techniques for Llama 3 verifiable inferences and achieve a significant speed up. And Syscoin also used this to shrink the SP1 verifiable circuits. So the main technical contribution of today of our paper consists of two parts. First, we introduce a new lattice-based high-arity folding scheme, which is of independent interest. And the second, we introduce a simple compiler to convert this folding scheme into a succinct argument. The high-arity folding schemes allows us to reduce L, which can be up to 1,000 statements over polynomial ring RQ, into constant number of statements. The proving time is dominated by Ln ring operations for computing witness commitments. The memory size is linear in witness length n, but independent of L. The verifier time is linear in the number of statements, but logarithmic in the witness length. And here we do not account for the Fisher-Shamir cost because it won't affect the recursive circuit size later. As a limitation, our proof algorithm requires log n passes of the witness data because we need to run some chat protocol. After having this L-arity folding scheme, we next compile it into a succinct arguments for either L or L squared or even L to the C uniform statements. So we can support L to the C statements for any constant C. The compilation preserves the post-count security, time and memory efficiency of the folding prover. And even though we focus on lattice folding schemes, it shouldn't be too hard to extend this compiler to other folding schemes. Finally, compared to IVC and PCD approach, we emphasize again that there's no need to embed any Fisher-Shamir hashing circuits anymore, and the security can be proven in the random oracle model. Now let's dive a little bit more into the details, and our focus will be the last high-arity folding scheme. We start by following a standard framework initiated by Lattice-Fold and Hypernova. The prover starts by decomposing the witnesses into some no-norm vectors and then compute and send corresponding lattice-based commitments. For our targeted applications, witnesses are already no-norm by default, so we can omit this decomposition step. After that, the goal is to prove these MP and no-norm statements regarding the committed vectors. So to do that, the prover runs a memory-efficient and batched sum check protocol to reduce these MP statements and norm statements into some linear evaluation statements. And next, the verifier samples a no-norm random vector, and the prover uses it to linearly combine commitments, witness, and evaluation claims. And we end up with a single folded witness statement. The commitment computation here is memory efficient and streaming friendly, and also recall we use a memory efficient sum check. Now the key challenge is how can we fold multiple lattice-based norm statements into a single evaluation claim. Our goal is to design a much more efficient protocol that folds many approximate norm statements. By approximate range statement or norm statements, I mean that the prover may still succeed with some chances, even if it's using a slightly higher norm witness. And this means that in the knowledge soundness proof, the extract witness could have a slightly higher norm as well. But this is fine in our cases where the folding depth is low and we don't have too stringent norm requirements in applications. Now let's see how it works. First, let me recall the relation we want to prove. The public instance is a lattice-based commitment, and its witness is the integer coefficients of the underlying opening vectors, which are some ring elements. We say this relation holds true if the witness is the coefficient vector of a valid opening, and moreover, this commitment openings has a small infinite norm. The first technique we use is called structure projection, introduced by the Rock and Roll paper. Given a vector W of length n by d, n times d, we split it into many chunks of length d lambda chunks. Next, the verifier examples a random challenge, which is a small random matrix J of dimension lambda by d lambda. Given this matrix J, the prover will compute a projection of each orange chunk and obtain a smaller green chunk. Note that each component's projection reuses the same matrix J here. After that, the prover will combine all these small green chunks, and this gives us a new vector of length n, which we call U. By Johnson-Linden-Strauss lemma, we can reduce the norm check of the original vector into the norm check of its shrinked vector U. More precisely, we want to prove that W is a valid opening to the commitment, and its transformation of W, which is U, is also a no-normed vector. Given that, the next technique is to fold these projective vector statements. And then this is inspired by the monomial check protocol from Lattice-Fold Plus. For simplicity, let's consider an even simpler task, which is just to check that each element of U is between the range of 0 to d-1, where d is the degree of the polynomial ring. And this idea can easily extend to support larger ranges. So first we fix a polynomial t, which we call table polynomial, where the coefficient of each monomial x to the d minus I is minus I. And the key observation is that this simplified norm statement is true only if there exists another commitment to some monomial vectors delta, such that for every index I from 1 to n, ui is exactly the constant term of this multiplication between tx and delta I. It's not hard to see that if this holds true, ui must be in the range. because given the structure of the polynomial ring, the constant term of this multiplication must be the negation of one of t's coefficients, which is in the range of 0 to d minus 1. Given this observation, we adapted Lattice-Based idea and introduced a new simple sum check that reduced these statements into linear statements of W and delta. The prover is dominated by n ring additions and an ON size sum check protocol over a lambda B field. And the verifier involves only OD plus log n field operations. We note that this protocol is approximately d times cheaper than in Lattice-Based because we only need to range proof a d times smaller vector u here. And I want to mention that the resulting scheme is relatively simple to describe. However, we carefully leverage some algebraic techniques for efficiency optimization, such as tens of rings. And also this knowledge sums proof turns out to be less trivial than in the prior work. And refer to our paper for more details. After knowing how to build high-arity folding schemes, now let's see how to convert it into a succinct argument. Our main result is the following. Assuming the hardness of module shortest integer solution problem, and given a L-arity lattice folding scheme, and any commit and proof SNARKs in the random oracle model, which is a special class of SNARKs where you can commit data first and later efficiently prove relations over the committed data. Given these three building blocks, we can obtain the succinct arguments of knowledge for L uniform statements, each of witness size n. And this can be generalized to support L to the C uniform statements based on a slightly stronger modulo C-like assumption. And notably, this recursive circuit size here is only linear in L, but not linear in M. Here, the prover memory size is independent of the number of statements you prove, and time is almost linear in N times M, which is the number of statements you prove. The verifier's complexity is polylogarithmic in N plus the cost of reading the input instances, which is about 32 M bytes if we compress inputs using collision-resistant hash function. But still, this is a limitation because public inputs can be large if we set M to be too large. That's why in practice, I'd recommend using M to be less than 10,000. Additionally, we can somehow view this framework as a generalization of the double commitment framework introduced by the prior work, such as Labrador. But the key difference here is that commitments used in this commit and proof SNARK here do not have to be a lattice commitments and doesn't even have to be nearly homomorphic. For example, we can use a hash-based SNARK. Beyond that, we introduce also further optimizations to minimize the recursive statement sizes when the folding depth is larger than 1. And as I mentioned here, this can be, we can make it to be independent on the number of statements we prove. Okay, for time reason, I will wrap up here. In summary, first we build a lattice-based high-arity folding scheme that allows log m path proving algorithm with fast and memory efficient prover. The scheme is also plausibly post-com secure. Second, we convert this high-arity folding scheme into a succinct argument of knowledge, which is a generic and modular compiler with small recursion overhead and allows security proof in the random oracle model. There are also many interesting open problems. First, can we obtain a one-pass high-arity folding schemes that is also memory efficient? Second, can we make the folding verifier circuit size even smaller, for example, even sublinear in L? Third, can we make the public input size a constant size for iterative computation in this framework or in some other framework other than IVC or PCD? Finally, it would be nice if you can have a security proof in the quantum random oracle model, which increases the confidence of its post-com security. These are all very intriguing questions that was exploring. And thank you for listening, and welcome to check our latest version of the paper, which includes some new revisions and optimizations. Okay, so that's it. And thank you for listening. And now I'm happy to take more questions.
Offering. So if so, if you have more questions, I think you should ask Binyi directly. No, so he offered to be online, but at the end it was not possible. So I think we conclude the session. So see you everyone tomorrow.